So it's my pleasure to introduce Balthasar Grabmayr from the University of Tübingen, and he's going to talk about metamathematics with his talk on the limits of mathematics and their philosophical consequences. Thanks again.
Thanks, Leon. And it's really a great pleasure to be here. Okay, so there are three fundamental methods in mathematics, namely proving theorems, defining mathematical concepts, and calculating functions. And today I would like to ask about the limit of these methods. And more specifically, I would like to ask the following questions, which, as you will see, are also of philosophical significance. First, can we prove that mathematics is consistent? Second, can we define a notion of mathematical truth? And third, can we mechanically check whether or not a given sentence is logically valid? And here I'm concerned with what is possible in principle on purely logical grounds. So, for example, what can be mechanically checked given an unlimited amount of time and space? And due to the pioneering efforts of logicians like Tarski, Turing, and Hilbert, we have precise explications of these idealized concepts, that is, of proofs, of definitions, and of calculations. And so this allows us to rigorously study the limits of mathematics. And since we can use mathematics to study itself, this field of research is also called metamathematics. And in the first part of the talk, I would like to introduce some important results of metamathematics, focusing on the case of probability. And then in the second part, I will argue that even the most powerful and general versions of these theorems, or of these results, which we find in the literature, suffice to settle our questions regarding the limits of mathematics. And roughly, this is because the precise metamathematical theorems are formulated and proved relative to specific formalization choices, while the philosophical interpretations are in some sense formalization free or formalization independent. And then the main task of today's talk will be to examine the extent to which we can narrow or even bridge this gap by abstracting away from the underlying formalization choices. And then I will show in the third part that we can do that in the case of the famous limitative results due to Gödel, Tarski, and Church. So here we can really get some deep answers regarding the limits of mathematics. And then as a counterpoint in the last part, I would argue that this gap cannot be narrowed in the context of certain type-free truth theories. So here we should be very skeptical when we take these results to bear on the limits of mathematics. And the last part is based on a joint work with Balthasar. Okay, today I will give only an overview of some recent results without going too much into technical details, but please feel free to press me in the Q&A, and then I'm happy to unpack a bit what I'm speaking here. And also you can consult one of these papers if you're interested. And before we can study the limits of probability, let me say a few words what exactly proofs are. So the idea is that we start with certain sentences we just assume without proof. We call them the axioms. So for example, in piano arithmetic, we assume without proof that 0 is a natural number, that 0 is not equal the successor of any natural number, and so on. And piano arithmetic is some formal number theory, which will be quite central in this talk. And then we lay down logical rules, which allow us to derive new sentences from these axioms. So you can think of the proof as a complex object which is put together from axioms in a certain regimented way. And a proof allows us to establish the truth of a sentence with logical certainty, given the truth of the axioms. And since antiquity until the beginning of the 20th century, mathematicians widely believed that for every sentence we can either prove it or disprove it, at least if we try long and hard enough. However, that belief was shattered in the 1930s by Gödel, who showed that there are fundamental limits to what can be proved. And more specifically, Gödel showed that there is an arithmetical sentence or a sentence of number theory that is true, but unprovable. And even worse, Gödel showed that no consistent mathematical theory can prove its own consistency. That means, in particular, that we cannot prove the consistency of number theory using arithmetical methods. And you might think that sounds puzzling because number theory is concerned with numbers and not with groups or consistency, right? So consider the following claim: there is no largest prime number. This is a claim about numbers, and it can be formulated and proved in piano arithmetic. In contrast, consider the claim that piano arithmetic is consistent. That is, the claim that there is no proof in piano arithmetic of the contradictory formula 0 equals 1. This is not a claim about numbers. This is a claim about formulas and proofs. And as you can see on the slide, they reside outside the world of arithmetic. So the question is, how can we make sense of the claim that PA does not prove its consistency? And so in order to turn the consistency claim into a sentence of number theory, we will devise a method that assigns to every formula and to every proof a number which serves as its code. And such an assignment, which establishes a correspondence between syntactical objects and numbers, is called a Gödel numbering, or a Gödel coding, as I would say. So you can think of such a coding just as a machine, which transforms all kinds of objects, bananas, chairs, into numbers. And in particular, that machine translates formulas and proofs into their Gödel codes. So the idea is that we can somehow like encode or like express a complex mathematical idea by a single number using this method. And while in the 1930s, it took like a genius like Gödel to come up with such an idea, today codings are part of our daily life. So think, for example, of your Word document, which is encoded by a long sequence of zeros and ones on your computer, and where all your manipulations and copy-paste edits correspond to certain arithmetical operations on these binary sequences. But in a very similar way, since every formula and every proof has its code number, we can arithmetically express properties about formulas and proofs. And using that, we can construct an arithmetical formula, PR for provable, that satisfies exactly the code numbers of provable formulas, right? And in that sense, this formula expresses probability in piano arithmetic. And that's why we also call it a probability predicate for piano arithmetic, or in short, for PA. And now, using such a predicate, Gödel formulated the statement that this sentence is unprovable in PA in purely number theoretical terms. Now, sentences of arithmetic are either true or false. So let me ask you, whoever thinks this sentence here is true, give me a thumbs up. Whoever thinks the sentence is false, give me a thumbs down. Think about it. And it's false. Okay. You're not convinced that every arithmetical sentence is either true or false? Okay, let's check. Well, let's assume that the sentence is false. Then it's not the case that the sentence is unprovable, so the sentence is provable in PA. But now, if a sentence is provable in PA, then it must be true. This is the way we set up our proofs. So we have shown that if the sentence is false, then it must be true. So it must be true, right? We have shown that the sentence must be true because it cannot be false, because that would entail that it's true. And now, since the sentence is true, we can also moreover conclude that it is unprovable, because this is exactly what the sentence says, right? The sentence says that it is unprovable. And here we have, by the way, Gödel with his sentence, but in Gödel's defense, this is my handwriting. So the result that there is an arithmetical sentence that is true but unprovable in PA is called Gödel's first incompleteness theorem. And in fact, it's much more general because it holds not only for piano arithmetic, but for every consistent and sufficiently expressive mathematical theory. And basically, the theorem shows that it is impossible to devise a universal theory which proves all the mathematical truths. Okay. Now, even worse, Gödel showed that piano arithmetic does not prove its consistency. So let's look at that sentence here. Piano arithmetic does not prove the sentence which says that the contradiction 0 equals 1 is not provable in PA. And here use these coin corners to denote the code of a formula, right? Okay, and while the mathematical correctness of Gödel's results were immediately accepted by his peers, their philosophical consequences remain to be a very central and much debated topic in the philosophy of mathematics to date. So let me discuss them. And for starters, I would like to clearly distinguish between Gödel's theorem, which says that a specific sentence of piano arithmetic is not provable in piano arithmetic, and its philosophical interpretation, according to which piano arithmetic doesn't prove its consistency. And as opposed to the formal result, right, to the theorem itself, the philosophical interpretation is formulated in a technical fragment of natural language, one we typically use when we engage in philosophical studies. And so it's not a surprise that it is not the theorem, but the philosophical interpretation of the theorem that is frequently applied in philosophy. So, for example, the philosophical interpretation of Gödel's second theorem has been used to show that Hilbert's program in the foundation of mathematics is untenable. In the philosophy of language, people like Shapiro, Catlin, Leon Horsten have argued, based on the philosophical interpretation, that inflationist conceptions of truth are inadequate. And also, like, this interpretation has been applied in the old debate whether or not the mind is a machine. There are many more applications. And of course, much can and should be said about these applications, but the primary concern of this talk is to ask how this philosophical interpretation can be justified. Again, note that the philosophical interpretation is not identical to its underlying theorem. And so I want to ask how we can infer IG2, which is the philosophical interpretation, from the underlying theorem. And the importance of that question has already been stressed, for instance, by David Auerbach, who writes that, I quote, "The philosophical interpretation of Gödel's second theorem is the usual material for philosophical writings concerning the philosophical significance or consequences of the Gödel second theorem. Since the philosophical interpretation isn't the mathematically proved second theorem, such writings would be held by an argument that IG2 interpretation is true." And that's exactly what we want to do in this talk here. And I claim that the inference from G2, that is from the theorem, to its interpretation is not valid. And that is because, let's look at Gödel's second theorem, it does not rule out the possibility that PA proves a different sentence that also expresses the consistency of PA. So the point is that that particular formula here is one of infinitely many ways of expressing consistency, but Gödel's second theorem only establishes that one of them is unprovable. And so I claim that in order to justify the philosophical interpretation of Gödel's second theorem, we actually have to show that every sentence that expresses the consistency of PA has to be unprovable in PA. Okay? That's what we want to do. And this requirement naturally brings us to a very well-known generalization of Gödel's second theorem, which is due to Hilbert, Bernays, and Löw, and which says basically that PA does not prove any consistency sentence that is based on a probability predicate that satisfies the so-called Löw's derivability conditions. Okay, let's just have a brief look at them. So we have three clauses. The first one basically says that if PA proves phi, then PA should also prove provable phi. The second one can just be thought of as a formalization of modus ponens. And the third one can be seen as a formalization of the first clause. And typically, these conditions are taken as absolute minimal conditions every reasonable probability predicate should satisfy. So in particular, the theorem due to Hilbert, Bernays, and Löw is taken to show that that like we cannot prove any consistency sentence in PA, right? But now there's a problem. And the problem is that Löw's conditions are formulated relative to a specific arbitrarily chosen coding. So I mark these in red, right? All the occurrences where we use like coding. And now the above theorem due to Hilbert, Bernays, and Löw does not show, or does not exclude the possibility that PA proves a different consistency sentence, which is formulated relative to a different coding. And indeed, there are infinitely many codings. So there are infinitely many ways to assign numbers to one and the same proof or one and the same formula. And so I argue that in order to justify our philosophical interpretation of Gödel's second theorem, we need an even more general result. Namely, we need to show that the underlying theorem, Gödel's second theorem, holds for all codings. Okay? And before I tackle that challenge, I would like to draw now a parallel to Tarski's theorem, which is widely taken to show that there are limits to what we can express or define. So let's look at that theorem. It says that the set of codes of true sentences of arithmetic is not arithmetically definable. So like using an arithmetical language, we cannot define its own truth predicate. And this theorem is widely taken to show that the set of all arithmetical truths is not arithmetically definable. Okay, that's like the philosophical interpretation of Tarski's theorem. And again, it is the philosophical interpretation and not the underlying theorem that has been applied in philosophy. So Giacinto, for instance, uses the philosophical interpretation to argue against formalistic conceptions of mathematics. Let me quote, Tarski showed that no arithmetical predicate represents the property of being a true sentence of arithmetic. If, as seems plausible, all purely formal properties are representable in arithmetic at some level, truth in the language of arithmetic cannot be reduced to a formal property, right? So it's just important to see that, like in the first line, here Giacinto uses the philosophical interpretation and not Tarski's theorem itself. But now again, you observe that as in the case of Gödel's second theorem, also Tarski's theorem depends on the coding, right? Recall we said the set of codes of true sentences of arithmetic. And so this theorem does not rule out the possibility that we can define truth if we change the coding, because Tarski's theorem is formulated and proved with respect to specific coding. And so once again, I claim that the inference from the theorem to its interpretation is not valid. And in order to justify the philosophical interpretation, which is coding free, we have to show that the underlying theorem holds for all codings. So what have we done so far? I have shown, we have seen that the philosophical interpretations of Gödel's second theorem and Tarski's theorem, and not the underlying theorems themselves, are of high philosophical relevance. And in order to justify them, we need to prove the invariance of the underlying theorems regarding the chosen coding. And that's what we're going to do now. So how can we formulate the invariance of Tarski's theorem? Well, we can just formulate it as follows for each coding alpha. And that is for any injective functions from formal expressions to the numbers. The set of alpha codes of true sentences is not arithmetically definable. That's a nice way of formulating the invariance of Tarski's theorem. So in order to formulate the invariance of Gödel's second theorem, we first just make explicit the used coding in the formulation of Löb's conditions. So we say that the formula provable satisfies these Löb conditions relative to some coding alpha, just if these three clauses are satisfied. And I just add an index here like alpha to highlight that now we use the coding alpha in this formulation. And then we can formulate the invariance of Gödel's second theorem as follows. PA does not prove any consistency sentence that is based on a probability predicate that satisfies Löb's conditions relative to some coding. Okay, so we now have invariance claims for both results, but they turn out to be false. Okay, so Tarski's and Gödel's theorems do not hold for all codings. More specifically, we can construct a coding alpha and a probability predicate, which satisfies Löb's conditions relative to alpha, such that the probability predicate gives rise to a provable consistency sentence in contradiction to Gödel's second theorem. Moreover, we can come up with a coding beta and an arithmetical formula that defines the beta codes of true sentences in contradiction to Tarski's theorem. And the cheapest way of constructing such numberings, such codings, proceeds as follows. So I just focus on the first case of the alpha. So the idea is that we start by just enumerating all the theorems of Beyond arithmetic. And we also enumerate all the other expressions. I call them the non-theorems. Okay, all the other expressions of our language that are not theorems of Beyond arithmetic. And then we just assign the number 2n to the nth theorem, and the number 2n plus 1 to the nth non-theorem. And we can see that the codes of the theorems are precisely the even numbers, right, on the left column here. So we can now just pick the formula which says that x is an even number as our probability predicate. And we can check that indeed it satisfies Löb's conditions. And we can also check that, well, PA proves that the code of 0 equals 1, which is odd, is not an even number. But of course, PA can prove that an odd number is not even. So we have a provable consistency sentence. And now, of course, these choices are fundamentally flawed, right? I claim that alpha and beta are inadmissible choices in the formalization process because, intuitively speaking, their definitions seem to rely on resources that exceed the given formalism. So in the case of alpha, for instance, we can note that the definition of alpha relies on a decision mechanism, whether any formal expression is provable or not. But that's inadmissible. I mean, we want to understand, we want to study the limits of what is provable or not. Therefore, we shouldn't take that for granted when we come up with the coding. That seems to be intuitively inadmissible. And so in order to exclude such deviant or inadmissible formalization choices, I require them to only employ the resources of the given formalism. Now that's pretty vague. What I mean by that is that in the case of Gödel's theorem, admissible codings only employ the resources of piano arithmetic. And by that, I mean that piano arithmetic can know or verify or prove certain facts about the coded syntax. And from that, I extract a precise minimal constraint that I call PA effective. I suppress the details. If you're interested, we can discuss this in the Q&A. What exactly is unpacked here? But the idea is that we have quite a minimal constraint called PA effectiveness for admissible codings in the context of the second theorem. In the context of Tarski's theorem, the requirement amounts to the following, namely our standard mode of arithmetic, the interpreted language, should be able to express and define certain facts of the coded syntax, and that can be made precise by requiring every admissible coding to be undefinable. Again, I'm suppressing what that exactly means. Okay, and then we can see that alpha and beta are not PA effective and undefinable respectively, and therefore the provable consistency sentence and the definable truth predicate they give rise to are philosophically insignificant. In particular, they do not refute our philosophical interpretations of Gödel's second theorem and of Tarski's theorem because they are flawed, they're inadmissible. Moreover, and that's nice, if we restrict ourselves to admissible codings, then we can actually prove the invariance of Gödel's second theorem. So we can prove that PA does not prove any consistency sentence that is based on a probability predicate satisfying Löb's conditions relative to some PA effective coding. And we can also prove the invariance of Tarski's theorem. So we can prove that for every undefinable coding alpha, the set of alpha codes of true sentences is not arithmetically definable. So we have succeeded in proving the invariance of both Gödel's and Tarski's theorem regarding admissible codings. And therefore, we have successfully narrowed the gap between the theorems and their coding-free philosophical interpretations. But in the next part, I would like to argue that in order to fully justify the philosophical interpretations of these theorems, more work is needed. Even more general results are required. And the reason is that so far I neglected another layer of formalization, namely notation systems. So recall that we showed that Tarski's theorem also independently of the coding of arithmetical formulas. But what actually is a formula? In other words, which notation system do we use when we formalize informal claims about arithmetic, like every number has a successor? And one option is to use infix notation. Maybe that's what you used when you had a course in logic. And And when we use infix notation, then we can formalize the claim that every number has a successor as this string here, right? But this choice is highly arbitrary. So alternatively, we could use Polish notation, where we write the operators before the operands. And what a nice feature of that is like that no longer brackets are required to ensure unique readability. We can use so-called piano notation, where we no longer have a primitive symbol for the universal quantifier, but we use auxiliary symbols instead, like brackets, for example. Instead of using variables, we may also achieve cross-reference between the quantifiers and their argument positions by drawing curved lines, such as proposed by Griman or Marquis. Another option is to base notations on parsing keys, or to use De Bruyn, I always mispronounce it, I'm sorry, indices, which specify the number of quantifier occurrences between the quantifier and its argument position. So you can see here, for example, the universal quantifier is linked to the argument position on the left side because there's one quantifier in between the path. And the existential quantifier is linked to the argument position on the right side because there's 0 quantifiers in between the path. That's like another notation system which is frequently used in computer science. We can also base notations on so-called S expressions, which are also the expressions of the programming language Lisp, and in a metamathematical context that we used by Clini and Pfefferman, or we go fully abstract algebraic, we just take expressions to be certain elements of certain free algebras. The point is, there is an abundance of different notation systems to choose from. They all can be found in the literature, actually many more, think of Regas and Griffschrift, for instance. So, as in the case of codings, Gödel's and Tarski's theorem are formulated and proved with regard to specific notation choices. And we know that they hold with regard to some standard choices, but they might fail with regard to others. And so in order to justify the philosophical interpretations of Gödel's and Tarski's theorems, we have to also show that the underlying theorems are invariant regarding the notation system. And as in the case of codings, we can come up with deviant notation systems that yield counterexamples to Gödel's and Tarski's theorems. But if we constrain ourselves to admissible notation systems, then we can actually prove invariance. So then we can prove that both Gödel's second theorem and Tarski's theorem are invariant regarding all admissible notation systems and all codings. And there's actually some interaction here, like the coding depends on the notation system, right? Because the domain of the coding, what is a coding actually maps the notations to numbers. So like there's some kind of technical complication here, which I omit, but I just wanted to quickly flag it. Okay, and we get a similar result with Church's theorem. And Church's theorem says that basically first order logical validity is not decidable. And so that gives us a limit on what can be computed. Okay, so let's take stock what I've shown so far. So we've started with like the observation that there is a gap between Gödel's, Tarski's, and Church's theorems on the one hand, and their philosophical interpretations on the other. We have seen that many philosophical arguments rely on the philosophical interpretations, not on the underlying theorems. And I claim that in order to justify the philosophical interpretations, we need to prove that their underlying theorems are invariant regarding admissible formalization choices. So invariance really guarantees that the underlying theorems really express a philosophical insight and not just some like artifacts of a conveniently chosen formalization. And I've shown that we actually can prove the invariance of Gödel's, Tarski's, and Church's theorems, and so we get robust insights into the limits of mathematics. Actually, there's a complication with Gödel's theorem. We can discuss this in the Q&A. Okay, and like now we just like might stop and rest assured that the choice of formalization really doesn't matter in metamathematics, or we keep asking, what about other metamathematical results? Is invariance perhaps some kind of universal law of metamathematics, or are there other metamathematical contexts in which the choice of formalization really matters? And it turns out the latter is the case. And in order to show that, Now, please permit me to jump to quite a different mathematical context, namely to the axiomatic study of truth. And as I mentioned before, this is based on a joint work with Balthasar. So let's start with the following two important informal principles of truth. So the first one says that the negation of a sentence A is true if and only if A is not true. And the second one, we call it disputational principle, says that a sentence of the form T is true if and only if T denotes a true sentence. Okay? And intuitively, these two principles are mutually taken inconsistent. And we can see this by like some informal arguments as follows. So we start with the liar sentence L, which says that L is not true. Okay, that's the famous liar sentence. And now since L is the very sentence, L is not true, L is true if and only if L is not true is true, right? So we just replace identicals. Now, by the first principle, we can conclude that L is not true is true if and only if L is true is not true. That's an application of the first principle of truth. And now applying the second principle, the disputational principle, we conclude that L is true is not true if and only if L is not true. So L is true if and only if L is not true, which is a contradiction. And now my question is, in which formal framework can we capture that reasoning? And so we have to formalize our informal principles of truth, as we usually do that in that field in theory of arithmetic. And we have to lay down and specify certain implementation or formalization details. And first of all, we have to specify an arithmetical signature, like the ideology, right, which will contain a unary primitive truth predicate. We have to specify a notation system, but for simplicity, I just keep the notation system now standard and fixed. We just take infix notation. We have to specify a coding of our infix notations. And we have to specify a numeral function, which maps numbers to their names in our language, right? Like we have numbers, but we want to also have names for that numbers like in our language, like the numerals. Okay, and with regard to these formalization choices, we can now formalize our informal principles of truth as follows. So the first principle can be formalized by the schema, which I just call not, right here, which says that not A is true if and only if A is not true, where A ranges just over L sentences. And you can see that schema is formalized using the signature, the numeral system, and the coding as a parameter. And the second principle, the disputational principle, can be formalized as one of the two schemata. So, well, basically the difference between these two schemata is that in the first version, we allow any closed term of the language to name a sentence. And in the second, more restricted version, we only allow certain canonical names, new numerals. Okay, that's the difference between these two schemata. And both perfectly fine ways of formalizing our informal disputational principle. And now we can take them together and build an axiomatic theory of truth, right? So T, which is based on the three parameters, is just like the first schema, not the disputational schema plus piano arithmetic. And the idea of why do we add piano arithmetic? Because we need some kind of background syntax theory, which like tells us properties about names and so on. And T asterisk is just a variant of our theory T, where we use the restricted disputational principle instead of the unrestricted one. And of course, different choices of the signature, of the numeral function, and of the coding will yield different axiomatic theories of truth. So now let's consider the following informal metamathematical claim, namely that the disputational principle, together with the commutativity of negation, together with the second informal principle, is inconsistent with the syntax theory PA. And this statement actually has been taken to bear on the study of truth deflationism. So this is relevant for philosophy. And if this statement is correct, then all reasonable formalizations of these two informal principles should be consistent, right? Because that's what the statement says. And in particular, our theories T and T asterisk should be inconsistent for all admissible choices of the signature, the numeral function, and the coding. Another question is, what are the admissible formalization choices in that context? Well, let's start with the signature. And I just take the following two very canonical signatures to be admissible. So the first one is the minimal arithmetical signature, which just contains a constant symbol for 0 and function symbols for the success operation, for addition, and for multiplication. And then we have the extended signature, which also contains function symbols for every primitive recursive function. And you find both of these signatures all over the literature. Now, what about codings? So in a study of untyped truth and self-reference, admissible codings are frequently required to be first effective and second of all monotonic. Effective just means that the coding is computable in some sense, and monotonicity amounts to the following property, namely the code of an expression is always larger than the codes of its sub-expressions. Okay, so here we have the admissibility requirements of effectiveness and monotonicity. Now, we clarified what are we have found two admissible signatures. We have some kind of constraint of admissibility for codings. What about numeral systems? And as opposed to the abundance of different codings, there are in effect only two numeral systems used in the literature, at least that I'm aware of. And the first one are standard numerals. I'm sure you're familiar with those. These just correspond to stroke notation of numbers. So the standard numeral of the number 3, for example, is just, well, we just have 3 occurrences of the successor symbol plus 0. But then there are also so-called efficient numerals, and those correspond to dyadic representations of numbers. And in order to clarify what that is, let me just give you an example. So here you have the efficient numeral of the number 13. And here you have the dyadic representation of the number 13. And I just want to point out the correspondence to kind of get you an idea how this works. So dyadic representations, right, we have either coefficient 1 or coefficient 2. And you can see that if we have coefficient 1, then we will have 1 occurrence of the successor symbol. And if we have coefficient 2, then we have 2 occurrences of the successor symbol. Well, that's very roughly how this works. So why would you use efficient numerals? And the reason is that sometimes we want to study very weak theories, which, for instance, do not prove the totality of the exponentiation function. But the problem is that the standard numeral function grows exponentially. So we cannot capture that in these weak theories, while the efficient numeral function only grows polynomially. That's a bit of a technical reason why sometimes efficient numerals are used in the literature. And here I take both standard and efficient numerals to be perfectly legitimate candidates for the notation, for the numeral function. Okay, and now, well, we can prove a theorem, and we can do that by extending work by Ricky Heck. We can show that there are monotonic and effective codings beta, gamma, delta, okay, such that our theory T, based on the minimal signature on either standard or efficient numerals and beta, is inconsistent, while the same theory, when we use the numbering gamma, is consistent. Similarly, we can show that the variant T asterisk, based on the extended signature, efficient numerals and delta, is inconsistent, while its counterpart based on gamma is consistent. So what does this show? Well, this shows that the constraints of effectiveness and monotonicity taken together are not sufficiently restrictive to actually determine the consistency of our axiomatic theory of truth. Okay. Now we can strengthen the theory, the theorem. So it also holds if you, for instance, require, well, admissible coding should not only be effective, but it should be much more effective than effectiveness. So for instance, they should be primitive recursive or Kalm elementary, right? That might be a way out, but it's not. Even then, the consistency remains indeterminate. And the theorem also holds if we strengthen the constraint of monotonicity in a certain sense. So that was basically a reaction of Volker Halbach. Volker Halbach said, okay, this is all fine, but if I require, for me, admissible codings have to have some kind of stronger notion of monotonicity, and then I'm sure the theorem breaks down. As it turns out, it's still, if we take these stronger like versions on like constraints and codings, then the consistency of T based on the minimal signature is still not determinate. What does this all mean? Well, recall that we had this informal claim here, which says that these two informal principles of truth are inconsistent. And we said if that is correct, right, if we want to justify that, well, all our theories based on admissible formalization choices have to be inconsistent. But now we see that even if we strengthen what is usually required of codings, then still this is not the case, right? We still cannot guarantee the inconsistency of these underlying axiomatic theories of truth. Okay. So I take this to raise doubts whether there are philosophically well-motivated admissibility criteria for codings which determine the consistency of these truth theories, but that's also a bit of an open invitation. So if your feeling is, well, admissible codings should have like an even more restrictive property, well, then we can see how does actually this affect the theorem. And as a result, the formalization of certain informal principles of truth in an arithmetical setting is highly sensitive to the underlying formalization choice. And we should therefore be careful when we claim that such axiomatic theories of truth faithfully capture some informal reasoning regarding our underlying principles of truth. Okay? The one we had in the beginning of the last part. Okay, so let's sum up. We've seen that the justification of the philosophical interpretations of limitative theorems requires invariance results. I mean, at least to try to argue that. We've seen that there are deviant formalization choices which yield counterexample to Gödel's, Tarski's, and Church's theorem. Well, the last case I didn't show, but by now you might believe me that this is also the case. And so invariance claims need to be restricted to admissible formalization choices. And admissibility criteria we shouldn't just stipulate, right? They have to be philosophically justified relative to the given mathematical context. And then we have seen that we can actually prove the invariance of Gödel's, Tarski's, and Church's theorems, and this provides us with philosophical insights regarding the limits of mathematics. But then as a counterpoint, I showed that certain results regarding untyped truth theories are actually highly sensitive to their underlying formalization choices. So we shouldn't take invariance for granted in mathematics. Okay, thank you very much.